Folks, this is Dr. Minders with your Mechatronic Systems 1 video. Today we're going to be talking about computer systems part 1. So remember last time we talked about electronic systems. We went through 4 different lecture sections. We talked about why do we need electronic systems. We talked about passive components like resistors and capacitors. We talked about active components like diodes and transistors. We interfaced transistors with resistors and LEDs and inductive loads. We talked about op amps. And then we also did a lab where we, what did we do in lab? We learned about electronic test systems, that's right. We talked about function generators and oscilloscopes and power supplies, and we're going to put that together with some more stuff in lab next Wednesday. But we're done talking in lecture about electronic systems, and we want to move on to the next big topic. So remember our Venn diagram here of what is mechatronics. We are good with mechanical systems. We've finished talking for the moment about electronic systems. We're skipping control systems for the time being. And so our next big chunk that we're going to talk about is computer systems. So, just like before, we want to talk about why do computer systems matter. We are going to, in this grouping of notes, we're going to talk about Boolean algebra, combinational logic, how we minimize combinational logic, and how we implement combinational logic. And then we'll follow that up in the future with sequential logic, which is an extension of combinational logic. And that's what we're going to get our software for our lab projects, and also, let's see, lab 6, I think, is now 5 is where we're going to implement the software. So we're going to be using this to build up to software, and also to build up to what is inside our microcontroller and our FPGAs, and what's the basis of how we implement control systems, for instance. So why do computer systems matter? So what I'd like you to do is humor me. Pause the video and think to yourself why computer systems actually matter. Write down some ideas. What do computer systems matter in your applications? Is it biomed? Is it seat design? Is it new product design somewhere else? What is your application area, and where do computer systems matter? Alright, so hopefully you wrote down something and paused the video and gave this some serious thought. So where do computer systems matter? Here are some ideas that I came up with, and this is not meant to be at all complete. So one of the things that we do with computer systems is we implement part-level feedback control. So for instance, we might design a controller such that our motor moves a linear device to and fro at a particular trajectory. We might also implement system-level supervisory control. So something like a finite state machine could be a system-level sort of control system without being part-level and worried about PID or frequency responses and the like. We might also do some signal processing. We talked about electronic systems being good for signal processing. Well, computer systems are too. It's a question of how you want to split up the signal processing. So you could do it either way, and certainly there are trade-offs. We might also want to communicate between different systems, and that may require some processing on a computer system. I didn't write this one down, but you might also use a computer system for design. It's not necessarily part of the implementation, but if you are designing your project, you're designing something that's going to grab a container of hazardous waste, somewhere you're going to sketch that. Maybe you're not going to do it all pen and paper, maybe you're going to use a computer for that, and that's honestly part of the whole mechatronics package. So, knowing that we're going to use computers, we need to know how a computer works, at least a little bit. And so we need to understand the difference between digital and analog representations of numbers. And I know you've seen this before, but it's always worth thinking over again. Remember that your digital implementation of numbers, we're talking about zeros and ones. Why is that? Well, because we're going to talk about logic here in a little bit. Analog representation is more like the number pi, where it's not easily quantified into, that's a bad way to put it. How about has infinite precision. How's that? A third, for instance, it has a repeating number. So what are the advantages and disadvantages of these different types of representations? Well, let's start with digital. Digital representations are less susceptible to noise, and that's something you're going to see here when we talk about noise margins. But essentially, if it's a question of a 0 or a 1, you've got some room on either side there before it flips over. But if you're talking about 3.14 and that 0.14 maybe slips to 0.15, you have some potential for noise problems. Zeros and ones are very easy for a computer to manipulate. So when we put it into our computer, crunch some numbers through MATLAB, it works better. MATLAB's not great at handling pi, for instance. However, just like you would expect, kind of the reverse here, we don't have infinite precision. We've got finite precision with ones and zeros. Everything, because everything's truncated to ones and zeros, if you've got something between 1 and 0, well, there's no way to represent that. You have to slide it one way or the other into a 0 or 1 bucket, so everything is finite. We also lose information when we sample, and this is partially because of our finite precision. That again, if it's somewhere between, you just have to pick which one it's going to go to, and so you've lost some information. But you also lose some information in that when you are sampling, and this is because you're going to be taking measurements periodically to put them into the computer. There's that time gap, and the time in between you typically lose. And when you're taking that measurement, there's also going to be a little bit of time between when you start and when you finish the measurement, so you're losing information all over the place. Is it significant? Well, maybe. It depends what you're doing. Yeah, there's a time lag. That's what I just said. In your sample and hold, there's a time associated between the start and the end of the measurement. And you can flip these around and put them into the advantages and disadvantages for analog. It's exact. You've got infinite resolution. It's instantaneous. That's wonderful. But you have potentially problems with noise and repeatability, and you can't manipulate them very easily in a computer. So the real world is analog. The representation of it that we will use for lots of things is digital, and we want to know how to manipulate digital numbers. So digital numbers lead to digital logic. So what is it? What do we mean by quantizing a signal? If we've got some group of numbers, say the real numbers, and we want to chunk them up into some smaller set, we might pull out the integers. And so we might say, okay, the integers are going to be a smaller set that's easier for us to deal with. And so we might choose that everything between the integers gets shifted one way or the other. So 2.3 gets shifted down to 2, and 2.6 gets shifted up to 3. And so we've taken our large, difficult to deal with set of numbers, and we've pared it down to a smaller set of numbers that is easier to deal with, but not quite as fine as the original one. And we could do this again with any multiple of q. You know, we could chunk it into multiples of 0.1 instead of multiples of 1, and we can get perhaps in that case a larger grouping of numbers, but more precise. And so whenever we do this, we want to worry about what happens when noise affects the quantization. We want to make sure that the quantization level is bigger than the noise that we anticipate having. So for instance, if we've got a binary signal, then we're going to allow only zeros and ones, and we're going to talk a little bit more about binary. We're going to allow only zeros and ones, and so any value in the middle there is going to get shoved into one bucket or the other. But if we know that we've got some noise, we want to make sure that it's clear which side it ends up in. And so what we want to worry about is what's called a noise margin, or the buffer zone. So if we've got binary devices, so we've got zeros and ones only, and the first device is sending a 0 or a 1 to the second device, This is a communication sort of thing. And if you send a 0, the second device automatically reads a 0. If you send a 1, the second device reads a 1, and this is pretty easy to picture here. There's nothing going on that's interfering with that ability to send a 0 or 1. But what happens when you add noise to the system? What happens when there's possibility that you're going to send a 0, but there's noise added in, and then you're not really getting a 0 anymore? What happens? Well, let's inject some noise between them. And again, we need to figure out how big our noise is and how much it's going to impact things. So if device 1 sends a 0, then if the noise is very small, say, I don't know, normal distribution with a, well, actually distribution is not a good idea. Let's say that it's noise that's no larger than 0.1. Then device 2 is going to get somewhere between negative 0.1 and positive 0.1, and how does it interpret that? Does that 0.1 mean a 0 or does it mean a 1? We don't really know unless we set up some sort of rules. Similarly, if we send a 1 with noise of 0.1, then we're getting something that's somewhere between 0.9 and 1.1, and how do you interpret that? Is that going to be a 1 or a 0? And what if the noise is really bad and a 0 ends up being a negative 0.6 or a positive 0.6? How do we read that? And so we really need to worry about this margin between the numbers. And so we call that the noise margin. And so if you look at the output and input lines here, the idea is that we establish a gap between the two. So for instance, on the output side, if device 0 or device 1 there is sending a value of 0, we know that from our noise margin spec, it's going to be somewhere between 0, and on this one, this is just an example, it'll be somewhere between 0 and 0.4. But if it's sending a 1, it'll be somewhere between, looks like 2.4 and 5 volts. So if there's noise injected on the system, then the output of device 1 could increase, significantly, but it still won't hit the high value. And so the second device is expecting anything for a 0 value. The second device is expecting anywhere between negative 0.5 and positive 0.8. So if there's some noise on the system, it'll still read it without misinterpreting things. And that gap in there, that space that we've allowed for the noise to fill, is what we call a noise margin or a buffer zone. And so for different types of chips, you can see that there are different noise margins between 0.4 and 0.7 and even 1.4 volts. So we do have to be careful and account for real-world effects that will cause our system to misread what our binary numbers mean. So assuming that we can read these numbers back and forth, what do we do with them? Well, we're going to talk about Boolean algebra, and this comes from George Boole, an English mathematician. And so Boolean algebra deals with variables that assume 2 and only 2 values, which really conveniently is what we're talking about with binary. And those values may be represented as 0 and 1, such as binary, or true and false, on, off, open, close, high, low. There's lots of different ways to talk about it. But certainly 0 and 1 is convenient. And these systems, well, let's see, general systems, like anything, like a mass spring damper system, an RLC circuit, these things can be static or dynamic, static being like a static mapping that doesn't require differential equations, where the output depends only on the current value of the inputs, and it can be implemented as a lookup table. Or dynamic systems which require differential equations, where you have to know past values of the inputs, and we have to worry about calculus. With Boolean behavior, we can do the same sort of thing. We can talk about static behavior, where we're going to deal with Boolean algebra, which is also called combinational logic. Or we're going to talk about dynamic behavior, where you need what we call sequential logic. And those are the two topics that we're talking about, the two big idea topics. We're talking about combinational logic today, and we'll talk about sequential logic when we build state machines. And like I said, we can represent this with binary, which is convenient. It doesn't have to be binary, but it's really convenient for our digital computing devices. So in Boolean algebra, we've got different operators. And so each operator, remember, is going to act on a variable that has only two possible values, exactly two possible values. And so those values are going to be represented here as zeros and ones for convenience. And so the not operator, which could be represented as x apostrophe there or x bar, is going to act on x, so x can be 0 or 1. And we'll put in a truth table in case you haven't seen one of these. So the truth table, we've got two columns here. The column that's already filled in, x, has two different values, 0 and 1, and so we'll fill in the not x column. So for x 0, then not x would be the other value, which would be 1. And for x being 1, then not x or other value would be 0. We can also make this into a mapping. So I know these bars are kind of hard to read on the slides. So x is on the top of our map, and x bar is on the left. So x can take on 0 or 1, and so x bar will give us 1 or 0. That's our not operator. We have and, or, and exclusive or operators. Again, in our truth table, we've got columns for each of these. So x and y are the first two, and then and, or, and XOR are the next three columns. So for instance, if we take that first row, we've got x is 0, y is 0, so x and y is 0. X and y, where x is 0 and y is 1, is going to give us a 0. Same for the next one. And the final one, x and y, where x is 1 and y is 1, gives us a 1. Or, oops, I guess I went to the maps next. If we put it in the map, it's the same information. It's just going to appear a little differently. We can fill in the ors. So 0 or 0 is 0. 0 or 1 is 1. 1 or 0 is 1. 1 or 1 is 1. We can fill that into our map as well, and we can do XOR. XOR is a little different. It's an exclusive OR, which means that AND case gets removed from it. We can fill it into our maps. So there's 4 of our operators. We can write equations using the operators in the same way that you have written equations in algebra. We still have hierarchy and parentheses that we borrow from our ordinary algebra. And it's a little different because we've got our dual operators. So if we've got zeros and ones swapped and our ands and ors swapped, then everything still works, which is kind of unique. So we've got these axioms that we can apply. Commutativity, if we've got x or y, it's the same as y or x. X and y is the same as y and x. We can do associativity, which is just like your algebra. We can do distributivity, which is also just like your algebra. We can do it either way here. And we know that there's a 0 and 1. This is our identity properties. And we've got complements, and we can write our complements different ways, a /x, x bar. There we go. And our complements being 1 and 0 depending on our operator. So these are our different axioms. We can take an equation, write it in a standard way, apply our axioms, and work out simplified versions. So given those axioms, then we can work out some useful theorems, and you can prove each of these. But these are all things that will be useful to you. The most important one probably for us is that last one, De Morgan's Law, which allows us to do some serious simplification. And also, one of the fun things with De Morgan's Law is when you go to implement things, it is sometimes very easy to implement with relatively cheap components if you use De Morgan's Law and put everything in terms of knots, and you'll see examples of that later. So how do we use this to write combinational logic? Well, what we want to do is we want to define a Boolean algebra for a system where we've got binary inputs, binary outputs, which is really easy to do because our computer systems with our digital input-output, those are all going to be zeros and ones when you read them in. And there can't be any history dependence or memory, so this is where we're restricted. But anytime if we can write something out that's static, we can do it this way. If we write something out that's dynamic, we'll take what we've learned here and apply it to sequential logic. So you'll see that. If you want memory, we'll do that next. So let's look at a simple example. If we've got a door lock, and we've got, say, a set of buttons, and we want to press the correct set of buttons, and in this case we're going to assume that there's only 2 buttons because that makes it nice and easy. And we want to press button 1, but not button 2, and then when we do that, the lock value is going to go from 0 to 1. And why do we want it to do that way? Well, because we want this to be unlocked, and so that's a convenient way to write it. So we'll draw a truth table. We've got B1 and B2 are 2 buttons, and what we said we want is that when 1 is pressed and 0 is not, or 2 is not pressed, then that's going to be unlocked. So there's our truth table. So the only case that we want to unlock on is that 1-0 case. Everything else, it stays locked. So how do we do this? Well, we can do it with sum of products, or we can do it with product of sums, but sum of products is the first one. So we will write this out as a sum of products, so a sum of different products of the inputs. And each one of those combinations, and we're going to write out combinations of the input and the complements, and I'll show you an example so it makes more sense. And then we will take out and we'll drop any of those that have an output of 0. So that's kind of doesn't make sense initially until we run through it. But this is the procedure. This is the basic procedure that'll build up everything. So for our 2-button lock, start with this. We've got B1, B2, and so we're going to write out the sum of products. So we take a product of B1 and B2. So that first row, we've got. Let me see if I can write on the screen here. So this first row, see, we've got a 0, 0. So there's our complements, not B1 and not B2. We've got 0, 1. So that is our not B1 and B2. We've got 1, 0. That is our B1 and not B2. And we got our 1, 1. That's our B1 and B2. If we write them all out, we just start with all of them. And then we want to get rid of any of them that have an output of 0. And so notice that we've got, let me see if I can get a different color. We got, this one is a 0. This one is a 0. This one is a 0. So let's throw those 3 away because they have outputs of 0. And the only thing left is Y is B1 and not B2. And we can test that. We can say, okay, remember that what we wanted was that B1 is going to be equal 1 and B2 is going to be equal to 0. So not B2 is going to be 1, and so 1 and 1 is 1. And so it holds true that the combination we wanted to program results in an unlocked case. And we can do this in a general case with lots of inputs. We can do this and it'll always work. It just may be sort of complex. We can also do a product of sums where we do exactly the dual of what we just did. So we write out the product of all of the sums of these terms. And then we'll drop any of them that have an output of 1. So let's do the same sort of thing. Ooh, my battery's running low. Let's do the same sort of thing. Let's take our various terms and put them in there. And let's throw away all of the ones that have an output of 1. And you notice that there's only 1 this time that has an output of 1. So let's throw that away. And the result, we can go through and we can test, but that's going to give us the exactly the same output of 1 for the same desired combination of 1, 0. And so in this case, you can see that the product of sums in this one is more complicated than the sum of products. And so, is it always true? No, it's not. It's very problem dependent. And so we want to be able to do is possibly test them both. They should both work, but there's not always a guarantee that one is going to give you a global minimum in terms of complexity. Now what we can do is we can do some minimization, and I'm going to show you some minimization techniques in the next video. But that will allow us to reduce the complexity sometimes, but there's not really guarantees in terms of in terms of what we're doing. There's not really guarantees that we're going to get an absolute minimum. So yeah, that's all I've got to start with. That'll get you going in terms of writing out some combinational logic, in terms of being able to take a relatively simple, no memory, Boolean input, Boolean output behavior, and encoding it into a set of, or an equation in terms of Boolean algebra. And we can take those Boolean algebra equations and we can implement them, and we'll talk about implementation in the third video of this set. Alright, stay tuned for the next video.